Hello, everyone. In this video, we're going to cover the workbook notes on section 2.1, and those are notes and examples on instantaneous rate of change and tangent lines. So let's go ahead and begin. So this first box asks us here, can change occur at an instant? So before we dive into the notes here, I just want to refer back to that pre-lecture activity where we looked at a car's display menu as it drove. So one thing that we noticed here, that you may have noticed here, is the different MPG displays. And what this brings to mind are the miles per gallon of the car as it drives over its long-term behavior. So over the full trip, what was the miles per gallon that was obtained over the entire trip versus at a moment in time, what miles per gallon were we getting? So over our entire trip, we can find this mile average, we might say miles per gallon, that isn't affected too much when we have big changes in the way we drive. So if we go up or down a hill, this average changes slightly. But say if we go up a hill, we're going to be getting a little miles per gallon versus going down a hill where we get more miles per gallon. We can cover more miles for each gallon. And so again, this brings up that notion between kind of long-term or average behavior and behavior at a moment or instantaneous behavior. So those are the two takeaways or important ideas that I want to emphasize here in this first box. So that is average rate of change versus instantaneous rate of change. And in looking at these two concepts deeper, we'll dive in more about what it means to have change occur at an instant. So let's just look at average rate of change. And you probably have seen this in a previous math course before, but let's look a little deeper right now together. So if we unpack this word average rate of change, let's think about what it might mean. So change is involved here. So change means how something varies over time, right? So whenever we're computing a change, we're computing a difference. What was the miles that we covered versus what miles did we start with? How tall was someone when they were 10 versus how tall were they when they were 8, right? We're going to subtract, take their height at 10 minus their height at 8. Whenever we find a computed change, we're thinking about a difference. So just keep that in mind when we're doing all of this work. So to talk about a change means to talk about a difference. And when we're talking about rate, we're wanting to compare two quantities. As in the example, miles per gallon, we're computing how many miles we're able to travel per gallon of gas. So we're comparing two quantities, miles traveled and gallons used. And then average is referring to a long or longer time trend. So we're going to be looking over intervals of these two quantities. So putting more detail into that, average rate of change, well, in order to compute an average, we need a measurable interval. So we need measurable intervals. So for example, that might be interval of gallons or a change of gallons used. Or time. Time is a typical example that we also use when asking questions about average rates. And then what does this look like? Well, if our function, say, is from x to y, we input an x and output a y. So x is, say, our input. We call y our output. Then the average rate of change is the change of y, often called delta here, this little change of y over the change of x's. How much does our output change given a change of the inputs? And so if we like, we've probably also seen notation using coordinates. So this would look like y2 minus y1 over x2 minus x1. So in this case, x1, y1, and x2, y2 are coordinates or points on our function from x to y. We've also seen this as a slope of a secant line, and I'll draw a little bit more about what I mean by that. Slope of secant line and this would be between the points x1, y1 and x2, y2. So let's look at a graph here. So suppose our graph looks like the following. And we have 2 points here. Say this is our first point. This is our second point. So in coordinates, this would be x1, y1, x2, y2. And our secant line is just a line going between those 2 points. Then the slope of this line would also be this quotient here, changes of y's over changes of x. And if we want to get even more detailed here, let's see, I'll label my coordinates further on my axes. So x's are on the horizontal axis and y's we'll put on the vertical axis. Oops, and I say I made a small typo there. We have y, x1, y1, x2, y2. And further notation, if our function is called f of x or f, then our output variables, I'm calling x's and y's, but often we also use, instead of x's and y's here, we use a's for our input, a's and b's for our input. Then our output, well, since it's a function of x, would be f of a, f of b. So just using different notation here, but really the same meaning of this slope or of this average rate of change would be f of b minus f of a over b minus a. So a few things that I want to highlight or emphasize here is that when we're computing this average rate of change, what we're computing is the change in outputs. So change of y, if you'd like, representing y's on vertical, or outputs. So change of outputs over the change of inputs, or over that interval of input. Okay, and then one more emphasis that I want to make here, this line I drew, that's what we call the secant line. Okay, so we can make sense of how we might describe the average change of a function over a given interval. And again, average change, so change of the function, how much the function increases or decreases over an interval of input. And that is average rate of change. So then how do we make sense of instantaneous rate of change? So this is something I encourage you to think about on your own and maybe meditate more over. But one thing involved in instantaneous or change at, or instantaneous rate of change or change at an instant is that we're now no longer over an entire interval. We're just considering the change of a function at a particular instant, at a moment in time. So if we think of our graph, go back to our graph here. I'll draw a new graph similar to the old one. But now the question we want to know is, what is change at a moment of time? So in this case, we focus on a particular input that I'll call, say, x1. So particular input. We want to know, well, how does the function change in that moment? So one thing that's common to do is to consider, well, let's consider average rates of change, like we had previously done. But now, rather than this big interval of input, we want to see what happens as that interval gets smaller and smaller. Another way of saying that is that change of x what happens to the change of the function as that change of x goes to 0. So writing down some notes here, I'll say instantaneous rate of change occurs at a moment, or rather at a particular input. Rate of change happens at a moment when referring to time, but it might occur at a particular gallon, for example, from our miles per gallon. So in instantaneous rate of change, we similarly look at a change of y over change of x, but now we look at this ratio as that change of x goes to 0. Again, as this interval of input gets smaller and smaller. So typically, notation that you'll see a lot is the following. So we'll have some x that we're interested in finding the instantaneous rate at. And then to represent this change of input, we would call this x plus h, where h is like a little amount away, or a little amount that we're going to consider going to 0. So h is the distance then between x and x plus h. So you start with x, and you add a little h to it, and you get x plus h. So going back to our, just keep continuing our notes here, we look at the interval x and x plus h as h goes to 0. So this is just different notation to describe the same thing, but we'll see why this is important in the next examples. And so then finally, what we want to consider are the slopes of these lines going through x and x plus h. And how do we represent those slopes? Well, change in output. So the outputs here would be f of x plus h and f of x. So the change of output, f of x plus h minus f of x over our inputs were x plus h minus x. So that just simplifies to f of x plus h minus f of x. And what's lovely here on the denominator, the x's cancel. So then we just have h in the denominator. And then we look at as h goes to 0. So graphically, what does this look like? Well, we start with our slopes of secant lines, where these secant lines kind of approach this one point. And then that final line that we get as we move closer and closer to our x that we're concerned about is called the tangent line. So that tangent line, there are many different ways that we can describe it, or many properties it has. But that tangent line is going to intersect our curve only once at that point of interest. And it will also be the best linear approximation to our curve, meaning it's a line, so it's a linear approximation to our graph that best represents our function within a small range around that point. All right, so at this point, I'd like you to go over any other parts of this video, or rewatch any parts of this video to make sure you have the complete notes here, and to review any bits of content. And when you're ready, feel free to move on to the next video where we explore an example to check our understanding.